1997. The Nobel Committee in Stockholm awarded the prize in economics to Black-Scholes and Robert Merton for a pricing formula that had already been running the derivatives markets for 24 years. Fisher-Black, the third architect of the model, was not there. He had died 2 years earlier. The Nobel Prize is not awarded posthumously. The most famous equation in quantitative finance has a body count and a Nobel Prize, and approximately $600 trillion of notional derivatives outstanding that price off of it every single day. This is it. The Black-Scholes formula for a European call option. Every quant knows it. Most people in finance can recite it. Very few can derive it from first principles. Almost none can explain why every single term is there. After this video, you'll be in that last category. No hand-waving. No, it can be shown. We show. Welcome to episode 3 of Quantifea. Let's go. Before we derive anything, let's be precise about what we're pricing. A European call option is a contract that gives the buyer the right, but not the obligation, to purchase a stock at a fixed price K, called the strike, at a fixed future date T, called the expiry. The payoff at expiry is max of S_T minus K, 0. If the stock finishes above the strike, you exercise and pocket the difference. If it finishes below, you walk away. The put is the mirror image. The right to sell at K, payoff is max of K minus S_T, 0. Both of these are trivially easy to understand at expiry. The problem is pricing them today. S_T is unknown. It's a random variable. The stock could finish at any positive value. You need to commit to a price, right now, for a payoff that depends on something that hasn't happened yet. Today you know, the current stock price S, the strike K, the risk-free interest rate R, the volatility sigma. You don't know where the stock will be at T. That's the game. People tried to solve this problem long before Black-Scholes. Louis Bachelier in 1900, in his PhD thesis, which his committee graded honorable rather than trace honorable, a slight he never recovered from, wrote the first mathematical model of option pricing. He used arithmetic Brownian motion, which allows negative stock prices. Not ideal, but a century ahead of its time. Paul Samuelson improved it in 1965 with geometric Brownian motion, which keeps prices positive. Better dynamics. Still no clean closed-form price. Then in 1973, Black-Scholes and Merton closed the problem permanently with a formula anyone can compute on a pocket calculator. Here's how they did it. Every model is a lie. The question is whether it's a productive one. Black-Scholes makes 4 assumptions that are all, to varying degrees, empirically false. And it's still the benchmark every options desk on Earth prices off of. Let's understand why. First assumption, stock prices follow geometric Brownian motion. We covered this in episode 2. Log returns are independent and identically normally distributed. Volatility is constant in time. What does this cost? Everything we covered in episode 1. Fat tails, gone. Volatility clustering, gone. Jumps, gone. Nassim Taleb put it bluntly. Those who gave us the normal distribution as a description of market randomness have a lot to answer for. He's right. And yet, second assumption, volatility sigma and the risk-free rate are a constant. This is perhaps the most operationally important lie in all of quantitative finance. Look at this. This is what the market implies about volatility across strikes and maturities, the implied vol surface. It's curved. It smirks. It has a term structure. It is emphatically not a flat constant. The Black-Scholes model has been wrong about volatility since October 19, 1987, Black Monday, when the crash permanently bent the smile into existence. It has never unsmiled since. And BS is still the benchmark. Make of that what you will. Third assumption, you can trade continuously, for free, in any size. This allows the delta hedge to be maintained perfectly, moment to moment, eliminating all risk from the portfolio. In practice, you rebalance daily or hourly. You pay bid-ask spreads. You pay market impact. The hedging errors accumulate. Taleb, who spent years on derivatives desks, called this the dynamic hedging trap. The theoretical perfection of continuous hedging dissolves the moment real friction enters the system. Fourth, no dividends, and the option is European. Both are fixable. Dividends can be incorporated via a continuous yield adjustment. American options require numerical methods, PDE or binomial trees. Extensions exist and are well understood. They're just not today's problem. So, for assumptions, all wrong, models still dominant. That's the power of a closed-form solution. People will tolerate a wrong model if it gives them a number they can act on and hedge with. Black-Scholes gives you that, which is exactly why we're deriving it today. Alright, this is the main event. We're deriving the Black-Scholes PDE, the partial differential equation whose solution is the formula. Every step will be explicit. The setup, stock price S follows geometric Brownian motion with drift mu and volatility sigma. The option price V is some function of S and T that we don't yet know. Our goal is to find it. Step 1. Apply Ito's lemma to V of S and T. We covered this in episode 2. The drift of V picks up 3 terms. The partial derivative of V with respect to time, mu S times the delta of V, and crucially, the Ito correction, 1/2 sigma squared S squared times the gamma of V, the second derivative with respect to S, plus a diffusion term, sigma S delta dB. This is the full dynamics of the option under the physical measure. Now we build the hedge. Step 2. Construct a portfolio pi, long 1 option, short delta units of stock, where delta equals the partial derivative of V with respect to S. The portfolio value is V minus delta times S. Why this particular delta? Watch what happens when we compute the portfolio's dynamics. Step 3. DPI equals dV minus delta times ds. Substitute the Ito expression for dV and the GBM expression for ds. Expand everything. Step 4. Look at the dB terms. We have plus sigma S partial V over partial S times dB from the option, and minus partial V over partial S times sigma S dB from the stock position. These are exactly equal and opposite. They cancel. Perfectly. Completely. That was not an accident. We chose delta precisely to make this happen. The delta is the exact hedge ratio that eliminates the randomness. And look, the mu terms cancel too. The expected return of the stock is completely gone from the portfolio dynamics. A portfolio of an option and exactly delta shares of stock has zero exposure to either the randomness or the expected return of the underlying. It is riskless. Step 5. A riskless portfolio must earn the risk-free rate. This is the no arbitrage condition. If the portfolio earned more than R, you could borrow at R and invest in pi indefinitely, a money machine. If it earned less, short pi and lend at R, markets eliminate both possibilities instantly. So DPI equals R times pi times DT. Substitute pi equals V minus delta S. Set the two expressions for DPI equal. Collect terms. Rearrange. And there it is. The Black-Scholes partial differential equation. Partial V over partial T plus RS times partial V over partial S plus 1/2 sigma squared S squared times the second partial of V over S squared minus RV equals 0. Every term has a name traders use daily. The time derivative, theta. The RS delta term, the discounted delta contribution. The gamma term, the Ito correction, the convexity of the option, the reason options have curvature in their payoff. The minus RV, the discounting. This PDE, combined with 3 boundary conditions, the terminal payoff, the value when the stock hits 0, and the deep in-the-money limit, has a unique solution. Finding it analytically requires one more trick. The PDE is in hand. Now we need to solve it. And we're going to use a trick that connects the 1973 Nobel Prize to a French mathematician named Joseph Fourier, who died 141 years before Black-Scholes were even born. The Black-Scholes PDE is a parabolic second-order PDE in S and T. It's not in canonical form. It has a variable coefficient s squared in front of the second derivative, and it mixes time and space derivatives in a way that's hard to work with directly. We need to change variables to simplify it. First substitution, let tau equal t minus t, time to expiry rather than calendar time. This reverses the time direction so that tau runs forward from 0 at expiry to t at inception. This is standard for parabolic PDEs. We solve forward from the initial condition. Second substitution, let x equal the natural log of s over k, the log moneyness. When s equals the strike k, x equals 0. We're centering the problem at the money. Compute the chain rule transformations for the partials. The second derivative in s becomes 1 over s squared times the second derivative in x minus the first derivative in x. This is where the log price substitution earns its keep. It converts the variable coefficient s squared term into a constant coefficient second derivative in x. Third substitution. Factor out the discounting. Write v as e to the minus r tau times u of x tau. This absorbs the minus rv term in the PDE. Substitute all three changes. After algebra, which I'll spare you the step-by-step of, it's in Shreve chapter 4. We arrive at this. Partial u over partial tau equals 1/2 sigma squared times the second partial of u over x underscore I squared, where x underscore I accounts for the drift. This is the heat equation. Partial u over partial tau equals 1/2 sigma squared times the second partial over 11 squared. Joseph Fourier derived this in 1822 to describe heat diffusing through a metal rod. The same equation governs how temperature profiles smooth out over time in a rod, and how option value diffuses backward from the payoff at expiry to the price today. The mathematics does not care about the interpretation. It's the same differential operator. The heat equation has a classical solution via its fundamental solution, the Green's function. The option price at any earlier time is the terminal payoff convolved with a normal kernel. Conceptually, we're taking the payoff at expiry, smearing it backward in time through a Gaussian filter, and the result is the fair price today. When you carry out this integral explicitly, substituting the call option payoff max of s underscore t minus k0, splitting the integral at s underscore t equals k, and evaluating each half, two terms emerge naturally. The first integral gives s times n of d. The second gives k e to the minus rt times n of d2. Transform back from u to v by multiplying by e to the minus r tau. And we have arrived. The Black-Scholes formula. Not from nowhere. Not from magic. From Fourier's heat equation, Ito's stochastic calculus, and the no arbitrage principle. 3 ideas from 3 centuries, combined into one formula. The formula is in hand. Let's take it apart, every single term. Because if you can't explain every component, you don't actually understand the price. The Black-Scholes formula for a European call is C equals S n of d minus k e to the minus rt times n of d2. Start with the simplest piece, k e to the minus rt. This is the present value of the strike price, what you will pay at expiry if you exercise, discounted back to today. In a world with no uncertainty, that's exactly what the option would cost. The interesting part is everything multiplying it. N of d2 is the risk-neutral probability that the option expires in the money, that s underscore t exceeds k at expiry. Not the real-world probability, the risk-neutral probability. Under the risk-neutral measure Q, where we've replaced the stock's actual drift mu with the risk-free rate R. More on that distinction in a moment. N of D is the options delta, the number of shares of stock you need to hold to replicate the option at every instant. It's also the probability of expiring in the money under a different measure, the stock measure, where we use the stock as the numeraire rather than the bond. These two probability measures differ by exactly the Ito correction. And here it is again, our old friend from episode 2. D minus D2 equals sigma root T. The difference between the hedge ratio probability and the exercise probability is the Ito correction. D2 uses the geometric mean drift, mu minus 1/2 sigma squared. D uses the arithmetic mean drift. The 1/2 sigma squared is permanently embedded in the Black-Scholes formula, as it must be, because Brownian motion lives in Ito's universe. Before we move on, put-call parity. It takes 30 seconds to derive. A portfolio of long call, short put, same strike, same expiry, must equal a long forward on the stock minus the present value of the strike. That's no arbitrage. No stochastic calculus required. Just the law of one price. C minus P equals S minus K e to the minus RT. If you know the call price, you know the put price. The two are not independent. The market respects this to the tick. If it doesn't, there's an arbitrage, and arbitrageurs close it within seconds. Here's the question that should be bothering you. When we derive the PDE, the drift mu, the expected return of the stock, disappeared entirely. The option price doesn't depend on whether you think the stock will return 5% or 50%. As long as sigma is the same, the option price is the same. This is not obvious. This is profound, and it has a precise mathematical explanation. The answer is the risk-neutral measure. Under the real-world probability measure P, the stock drifts at mu, its actual expected return, reflecting investors' risk preferences and compensation for bearing equity risk. Under the risk-neutral measure Q, we instead assume the stock drifts at R, the risk-free rate. Everyone is indifferent to risk. All assets earn the same return. The transition between these two worlds is governed by Gersonow's theorem. We change the Brownian motion by subtracting the market price of risk. Lambda equals mu minus R over sigma, multiplied by time. Under Q, the new Brownian motion makes the stock drift at R. This gives us the risk-neutral pricing formula. Option price equals the discounted expectation of the payoff under Q. This is the fundamental theorem of asset pricing, the deepest result in modern derivatives theory. Harrison and Krebs in 1979 proved that the absence of arbitrage is equivalent to the existence of at least one risk-neutral measure. Harrison and Pliska in 1981 proved that market completeness, the ability to replicate any payoff, is equivalent to the uniqueness of that measure. The Black-Scholes model is complete. One stock, one Brownian motion, one Q. The risk-neutral world is not a description of how investors actually behave. Nobody genuinely expects all assets to earn the risk-free rate. It is a computational device, a change of probability measure that makes option pricing tractable while preserving the no arbitrage constraint. The answer it gives is correct by construction. Do not confuse the risk-neutral measure with reality. Most people in finance don't. Because most people in finance if we derive Black-Scholes without telling you where it breaks. And it breaks, spectacularly, in at least one place. The volatility smile. If Black-Scholes were correct, every option on the same underlying, regardless of strike or maturity, would imply the same volatility sigma. That's what constant sigma means. You'd see a flat line across all strikes. What you actually see, in every liquid options market in the world, is a curve. OTM puts are expensive relative to Black-Scholes. OTM calls vary by market. In equities, you typically see a skew, a smirk, where out-of-the-money puts carry significantly higher implied vol than at-the-money options. This is the market pricing in the fat left tail, crash risk, that Black-Scholes says is nearly impossible. This phenomenon did not exist before October 1987. The 1987 Black Monday crash bent the smile into existence. It has never straightened since. The constant vol assumption has been empirically violated for 37 years. 3 reasons. First, fat tails. As we showed in episode 1, real returns have excess kurtosis, more probability mass in the tails than normal distributions predict. OTM options are worth more than BS says. Second, jump risk. Crash events are discrete, large, and fast, not continuous diffusions. OTM puts insure against crashes. They're valuable. Third, supply and demand. Institutional investors systematically buy OTM puts as portfolio insurance. This demand pushes their prices, and thus their implied vols, above Black-Scholes. The industry response was a hierarchy of increasingly sophisticated models. Derman and Connie in 1994 introduced local volatility, sigma as a function of both the stock price and time, calibrated to match the observed smile exactly. Heston's stochastic volatility model in 1993 makes vol itself a random process, a mean-reverting diffusion. Merton's jump diffusion adds compound Poisson jumps. All of these are extensions of Black-Scholes. All of them inherit its structure. None of them replace the fundamental insight. Here's the irony that professional options traders live with every day. Black-Scholes is wrong, and the market uses it as the unit of measurement. Traders quote option prices not in dollars. They quote them in implied volatility, which is the Black-Scholes sigma that makes the formula match the market price. The wrong model is the language in which the correct prices are communicated. This is either profound or farcical. For truths, I'll let you decide. The Black-Scholes formula is not magic, and it is not a black box. It is Ito's lemma applied to a delta-hedged portfolio, plus the no arbitrage condition, plus the classical heat equation solution. 3 ideas, all derivable in under an hour. All yours now. The expected return of the stock doesn't affect the option price. This seems wrong. It isn't. The risk-neutral measure explains it. Under Q, all assets earn R by construction, so mu is simply irrelevant to the pricing problem. Harrison and Krebs proved this rigorously in 1979. If you go into a quant interview and can explain why mu disappears, not just that it does, you are already in the top 10% of candidates. Black-Scholes has been empirically wrong about volatility since 1987. The smile proves it, and it's still the benchmark. Learn it deeply enough to know exactly how it's wrong, where it's wrong, and what the smile tells you about the assumptions it's violating. That knowledge is worth more than knowing it fails. Interview calibration. Can you derive the PDE from Ito and no arbitrage? Top 5%. Can you explain why n of D and n of D2 are different? Top 10. Can you explain the vol smile qualitatively? Top 20. Can you just recite the formula? That's everyone. Taleb wrote in Dynamic Hedging. The hedging errors are generally small for vanilla options, but can be monstrous for exotics. Know your model. Know its limits. Know when it fails. That's what separates a quant from someone who Googled the formula. That's episode 3. We covered the full Black-Scholes arc, the option pricing problem, and the century of failed attempts before 1973, the 4 assumptions and their real-world cost. The PDE derivation, Ito's lemma, delta hedge, dB cancellation, no arbitrage condition. The heat equation transformation that gave us the analytical solution. The anatomy of every term in the formula. The risk-neutral measure, and the fundamental theorem of asset pricing. And finally, where it all breaks, and what the profession built to replace it. 2 books, Hull's Options, Futures, and Other Derivatives, The Practitioner's Bible. Chapters 15 and 19 cover Black-Scholes as thoroughly as any textbook. Read it first. Then read Taleb's Dynamic Hedging, the book that tells you everything Hull's clean framework glosses over when you're actually on a derivatives desk running a book with real P&L. Comment challenge. Price a cash or nothing digital call. A contract that pays exactly $1 if S_T exceeds K, 0 otherwise. Use the risk-neutral pricing formula. The answer involves n of D2. I want to see the full derivation and an explanation of why only D2 appears and not D. First complete correct answer gets pinned. Next week, the Greeks. Delta, gamma, vega, theta, derived from the Black-Scholes formula by differentiation. We'll build every single one from first principles, explain what each one means economically, and talk about why gamma exposure is the most dangerous thing a derivatives desk can run. Your theta bleeds every night. Next week you'll know exactly why. Subscribe. Share this with one person who's ever pretended to understand Black-Scholes without being able to derive it. There are more of them than you think. This is Quantifea.